something.
Okay, I think it's going. All right. So if we take a quick skim through this, you'll see that it covers a decent amount of stuff relatively quickly. So the first page is just your basic, like, it might not pop out to you right away, but each one of those is a parent function. One of the famous parent functions, like the first one is x squared. The second one is square root of x. The third one is x cubed. The fourth one is cube root of x. The fifth one is 1 over x squared. And the fifth one is 1 over x. But they're all in some way transformed. So they're shifted left, right, up, down, flipped over, stretched, etc. So we'll go over those real quick. For number 2, same kind of thing. You've got another 6 functions. There's a couple snuck in, or at least there's one snuck in there. F is not really one of those parent functions. We'll talk about that one. Number 3, we'll be asking how many solutions exist for each one of these. So you pretty much want to solve those graphically. How many times, like, think about it in terms of crossing graphs. That's the way you kind of go through those. Number 4 talks about solving systems of equations. They're all nonlinear. So, again, it's finding the number of solutions. So again, you want to think about them graphically, but they're not all functions. A lot of them are just curves. So we'll definitely review that. And then from 5, 6, 7, 8, 9, 10, they're all kind of talking about transforming graphs in an abstract sense. So we're not going to give you a formula necessarily, but we're just going to make generalizations about some function. And so say I know something about f of x. What do you know about f of x minus 2? That kind of thing. And so you're going to take that idea of, like, well, I know that f of x minus 2 is shifted to the right. So what can I know about, say, points in the graph or the actual graph itself? And then 11, the dreaded absolute value transformation. Ooh, scary. Scariest one of them all. Because we all, I think, I don't know, shifting left and right, up and down, fairly simple. Replacing an x with a 2x is a lot of times a little confusing. That one throws people off. But replacing an x with an absolute value of x, that's one of the more confusing ones. So we'll definitely make sure we cover that. What do you mean?
Just review. I remember doing some of these things way later. Some of these earlier.
No, it's actually, believe it or not, it's actually in pretty much chronological order from last year.
It is so short.
It just feels,
Yeah, this is like a month of pre-calc
yeah, exactly.
crunched
Just like
into 2 days
Yes.
because we already studied it. So that's why it's crunched. Yeah. So you may find yourself in the position where you're like, I really don't remember this very well. It might require a little bit extra outside of time class to get brushed up on it. Obviously, if you ever want to stop in here and just questions, like you're like, oh, number 11 was really confusing for me. I feel like we went over the problems, but I didn't really understand it. I'd be glad to talk to you about those questions. We'll get you sorted out. You'll be fine. Anyway, number 12 is all about function composition. Doing f of g of x, f of x, things like that, f plus g of x. And that's pretty much the rest of the problem set until the last couple of questions are piecewise functions. So yeah, this covers quite a bit. And maybe there is, I'm trying to remember, maybe piecewise functions I did lump with limits last year. I can't quite remember. But this all fits together. It all fits together conceptually, hopefully. It's all about how graphs kind of fit together and work together and how they look. So let's get into it here. I don't think we need to let's just do maybe 1 or 2 from the front. That first question, how do you explain, how do you get from this graph to this graph? Hint, there are 2 transformations that took place. Who feels like they know the answer to this one? Rafe, what's the answer? How do you get from here?
It's moving down 1, right 4.
Very good. Right 4. Down 1. Okay. So if you were to graph this, it would look like 1, 2, 3, 4. Down 1. There you go. Feel good about that? Okay, great. So now I want to mention something real quick, because the thing that I feel like most students usually do pretty good with this when it's an actual, like we know what a parabola is. I just want to point out that what we're looking at here is basically going from a known f of x. So say you had the graph of y equals f of x, and then you were asked to think about the graph of, let me see if anyone knows this one. This is analogous to doing, did anyone complete this statement? Huh?
-4.
Very close. F of x minus 4 minus 1.
Yeah.
So this tends to be the harder thing for people to like sort of make sense of. But that's all we're doing here is we notice how we took this. This is my f of x. And we replaced the x with an x minus 4, hence the x being replaced with an x minus 4. And then we subtracted 1 from the outside of the function, hence the -1 on the outside of the function. So just keep that in mind there. That is a thing to be aware of. Okay? When you take calculus, or especially classes beyond calculus, they love to abstract things like this. They like to get away from an actual concrete function and start talking about, hey, if I give you some info about some nebulous function that lives out there, I won't tell you what it is, but some function out there, f of x, what can you tell me about f of x minus 4 minus 1? All right, so, that's for domain and range. So that should be fairly straightforward. The domain of this is all reals, right? Because the x value can be anything. How about the range? There you go. So there's a bottom to this parabola. You never get a y value below -1, so therefore the range is y value is greater than or equal to -1. Let's skip down to so real quick. So b is it's one of these guys. It's the square root function shifted left 4 down 1. C is this guy, cubic, shifted what direction? There's two things. Well, order of operations would say that first we shifted left 2. Not like it really matters in this case.
Yeah, left 2 and then
Yeah, so this one got shifted left 2 and then flipped over the x-axis, a vertical flip. What can we always do if say we're confused or we're not confident in our answer? Mr. Desmos is our friend. Okay, it's a good way to check to make sure we're doing everything correctly. So D is a cube root function shifted. What direction? Is it up, down, left, right? To the right. So cube root function, this guy. You can't really do it with your arms. I mean, everyone does the Egyptian thing, but that's more of like a, I don't know. I'm not sure what that would be like right, because the Egyptian looks almost like that, but a cube root is more like this. So maybe a more flexible person can do that with their arms, but I can't do it.
Where's Chloe?
Yeah. So E and F. So hopefully it's okay to skip to E and F. Maybe one more comment here. For C and D, those functions, there's something kind of special about them, which is, or at least one special thing about them is no matter how you shift them left, right, up, down, flip them, flop them, whatever, what is always true about it? Very good. The domain is all reals, the range is all reals, right? Because you start off with this thing where domain's all reals, range is all reals. I mean, if you shift them to the right, same thing's true. Shift them to the left, shift them up, shift them down. You get the idea. So no matter what you do to them, I guess there's one exception. What's a transformation you could do to this function where the range would no longer be all reals?
Value?
Huh?
Absolute value?
Yeah, you put absolute values on it. So for example, if you did, so x cubed graph looks like this. If you went absolute value of x cubed, that would turn all those y values positive, and you get something that looks like that. All right. So what happened? So first of all, who is E? Deep down, who is E?
Frame.
This is E. So, but what happened to him? What did the 4 do to him? Or what is, sorry, the 3 happens first, actually. What is the, so in problem E, what is the 3 doing? Well, the asymptote's already there because we're saying, so, well, you're right, Winslow, for sure. But if we're thinking in terms of transformations, you start with this guy. He's famous, right? He's already got, yeah, we know. Well, x equals 0 is an asymptote. I mean, so is y equals 0, right? In the end behavior. So there's 2 things that happen to it. First, we replace the x with an x minus 3. So what does that do? Shifts the entire structure to the right 3. So now this vertical asymptote is x equals 3. And then what does a 4 do?
Just makes it. Less steep. Yeah. Like line.
That's kind of an interesting question. I would say, to be precise, it multiplies every y value that occurred on this graph. Well, now they're all shifted over to the right 3, but they're all now 4 times bigger. So depending on, see, because I think technically it's more steep, but when you actually look at the graph, it actually looks kind of like wider and fatter. So it's a little confusing. So long story short, it's now every y value is now 4 times greater than it used to be. So what we usually will say is the 4 is a vertical stretch. That's the so we say a vertical stretch by a factor of 4. And then F, same kind of idea. What does F start off as?
Yeah.
This guy, but he got shifted
To
left 2, and then up 3. So he's gonna have 2 asymptotes, and those asymptotes affect the domain and range, right? So like for F, his domain is every real number except for -2. How about the range?
the range. X can't equal
Y can't equal 3. So the range is every y value in the reals except for 3. That can be a little confusing because people go, wait a second, you mean that +2 means the domain is x can't be -2, but then the +3 means the range is y can't be +3. And so, but yeah, that's what happens because the shift was left 2 and up 3. So before we move on, any questions on that, guys? Anything at all? Any questions? No? Good. Let's move on. Same thing on 2. I think we can skip 2 for now. I do want to talk about F. They all have, they're all just, it's basically another page of the same kind of thing. So a lot of these are like, so A, B, and D are all experience vertical flips over the x-axis. So that's something to keep in mind. There's a birdie in here. C's a birdie. Caw indeed. But I want to talk about F. Does anyone know? take a second. Maybe talk to your partner for 30 seconds here. Maybe try to come up with, if it doesn't occur to you what it looks like, maybe try to think of, can I think of one property about this function? Something relevant. You can do something really simple. Don't say it out. Just let everyone get a chance to think. When you see this little function here, can you come up with anything about it? It could be something, you can think big. I got the entire picture, or it can be really small, like I just know one point on the graph. Okay. Go ahead and thinky winky.
Yes, no. No. Yes. No. What is this? No, it looked like. It'd just be a G. Definitely, yeah. That's. No. Okay. So just that. Yeah, it's from board. And it goes, yeah, it's 4.
Okay, let's talk about it. A kind of peculiar way to think about this is it's take a parabola, flip it upside down, shift it up 16, and then plug it into a square root function. It's kind of a weird way to think about it, but it is a valid way of considering it. But who's got like a small property? Anyone got like something small? Just like I couldn't come up with much. Just like a kind of a basic. Huh?
Y-intercept 0, 4.
Great. That's a great answer. Okay. So if you plug in an x value of 0, the y value has to be 4. Is everyone okay with that? Okay. Anyone else got a small thing? Yeah.
Is there holes in this graph?
A hole usually occurs when you're doing, for example, a hole occurs on this graph. This graph would have a hole at 5. They happen a lot of times when you have 0 over 0. Terms, we'll study these a lot when we get to we review limits. So I don't think we're going to have any holes on this one. You certainly get some interesting behavior. What x value did you have in mind?
Like at 4, not 4, like 4 to 5, like as soon as it's changing at 4.
Oh, I like considering the number 4 because, right? Plug in 4, you get what? 0. But then you said 5 doesn't work, right?
Yeah.
What about 4.1?
Yeah. Wait, no. Wait, no.
How about 4.01? So you're getting there is some kind of math connection there between holes and what is happening there, but it's a little bit different. But basically, we're talking about domain, right? So the domain of this, I heard a couple of people say it in the murmurings. X cannot be, or X has to be less than or equal to 4, right? But what else? There's -4 as well, right? So X can't be the left of -4 because how about -4.1? Or maybe it's easier to think about -5. You can't plug that in there. You have a negative under the square root. So you get this. Okay, so interesting domain. We're so used to dealing with functions that have an infinite span of domain, whether it's from 0 to infinity or from -infinity to infinity. But this one just has the width of the domain is just 8. So that's a little unusual. Anyone else? I guess we're at this point. Does anyone know the answer? What shape it is?
This one.
Could be a reverse birdie. Could be a little pyramid. Here, spoiler. Suppose I had this.
Whoa, just like the top.
Oh, is that a circle?
So that's a circle, right? We're all good with that. that describes a circle. But if I solve that for y, subtract the x squared. Now, when you take the square root, technically, to get the full circle, you need plus or minus. So if I just take the plus version, which is what this is, I just get the upper half of the circle. So the range, of course, is numbers from 0 to 4. And this is a semicircle. Okay? Is everyone clear on what I was talking about? I said it kind of fast, but how the full circle would be. So this. A full circle would be technically this. The y values are plus or minus for every x value. This function, notice function, is just the positive version. So you just get that upper half of the circle. Hello, everyone. I think we're in pre-calculus. How do we feel about this? That review of like shifty, flippy, all that stuff. Feel okay?
Yes.
It's not.
Time is a flat circle. Right, Ave?
Sure.
Time is a flat circle.
Here's your evidence. Approved.
Okay. All right. So we've already talked about this a little bit. So this is kind of a re-review of this. But look at number 3. It's going to ask us questions like, how many solutions exist for this equation? Many. I'd say this is one of the neater things I think about learning to understand graphs is you can answer these kind of questions, Sorry, I just wasn't happy with that goal 3 there. And I think it's interesting to phrase the questions like, is there any number out there? Is it possible to come up with a number where the cube root of that number plus 1 is the same as dividing 4 by the square of that number? I don't know, it makes kind of phrasing it in a more riddle-like fashion, but in any case, here's an equation, and you might be wondering, does this equation have a solution? Is it possible to satisfy this equation? Go ahead and figure it out on your own. Get an answer. We'll check our answer, make sure we're all on the same page. Sigh indeed, Ave.
Did you want the actual math?
If you can find the solutions, then I will be really impressed.
I drew a picture.
It just says find the number of solutions that exist. If you can solve that by hand, I would be extremely impressed. I don't know if that's even possible. A computer can solve it. It's close to what?
Like 1 or 2.
Like
Like
just
just
a
hand
definite-
drawing it real quick.
Very good.
Yeah.
There's 2 solutions.
Okay, so hopefully you took this approach that I've been trying my best to get you to think about, which is, what if I graph this? Well, that is a cube root function shifted up 1. And I'm going to try to be, if I was doing this on a calculus problem, I would try to be a little bit precise. Not going to spend an hour drawing the graph or anything, but just at least make it sort of a precise looking, shifted up 1 cube root graph. And then this guy would have points like 1, 4. So when I say like make an accurate graph, just kind of generally along the right. This gives us a really nice proof, but it's very good evidence that it's like Aaron said, I know the answer is somewhere between 1 and 2. Because the graph seems to suggest that. Also, if you plug in 1, you get 2 equals 4, so the right side's too big. Then if you plug in 2, you get 1 plus cube root of 2, and then you get 1 on the right side, so now the left side's too big. So somewhere between 1 and 2, the left side goes from being smaller to being bigger, which you can see in the graphs, right? So he's bigger here, and then on the right-hand side of our solution, he's bigger. So, okay, so this also shows, are there any negative solutions?
No.
Okay, so what we showed here using graphs is that this equation, a weird equation, very difficult to solve by hand. A computer can solve it, of course, but I'm not sure. I'm sure there's an exact solution to this, but anyway, there's only one answer to it. It's a relatively small number, some number between 1 and 2, and there's no negative solutions to this solution. All right. So B, C, and D, I'll just leave those for you. C is kind of interesting. I mean, I think they're all kind of interesting, but C in particular might surprise you. But okay, let's look at 4. Same kind of thing, but they're not all functions. So looking at 4, is there a pair of numbers x and y such that x squared plus y squared equals 9, and also the y is the absolute value of x minus 7? So try that out. I'll give you a hint to that if you're stuck at all. If a pair of numbers x and y, if their squares add up to 9, then where do they live?
3.
True. Thinking visually here. If x squared plus y squared equals 9, then every pair xy lives on a circle, right? It's like if I say I'm thinking of two numbers and the x value, the y value is 2 bigger than the x value. Well, they live on a line then, right?
Yes.
Right?
Yes.
If the y value is 2 bigger than the x value, then they're like, where do you live? I live over here. I live on this line.
Well, I drew the best circle. I guess.
You drew the best circle of your life? That's good. Something to be proud of. Okay, so who got the answer to this? Anyone? How many solutions are there? None. Now why? Let's see. 1, 2, 3. You don't have to draw hash marks if you don't want. I think it's helpful for a question like this because it really will help me visualize. This is 3, so the circle's radius is 3, but this absolute value is shifted way over to 3, 4, 5, 6, 7. And I know that the slopes of these arms are -1 and 1. So I can see it is impossible. There's no pair of numbers that works for this because the graphs never cross. You okay with that? All right, so let's look at B. Do one more together. What shape do you get if you have a difference of squares? If it's like x squared minus a basketball?
No.
It's funny. I like that. No, I know what you're talking about.
Thank you.
I just never thought of that.
Well, if you look at the graph and then when it has the x in front, use the y-axis to go around it.
Okay, so this is a hyperbola.
It's a hyperball.
Now, if you're like me, I haven't like memorized. Oh, I have some mnemonic. If I see it, I have memorized it, I guess, enough that I recognize the structure. Okay, x squared minus y squared equals number. It's a hyperbola. then I go, okay, how's it oriented? Well, let's see, what's the pairs of numbers at work? Like, how about, could x be 2 and negative 2 when y is 0? So you get the idea? From there, you can kind of piece enough together to figure out what it looks like. My drawing's not great. It's not like you have to be an expert in hyperbola drawing, but
Necessary requirement.
yeah, that's nice. Huh?
They never had it on John Irving for being
Draw 10 hyperbolas.
Perfectly.
But I'm trying to at least draw them kind of good, because if you recall that idea behind the asymptotes, maybe someone can make me happy here. What's the slope of that asymptote?
1.
Very good. 1. Wow. How'd you know that, Aaron?
Because y equals x is the equation for the line, so it's just a rise of 1 and a run of 1, so it's just 1.
Okay. Yeah, if you rearrange this, you get y equals plus or minus square root of x squared plus 4. I'm sorry, minus 4. Sorry about that. And so as x gets large, so as x gets really large, the equation approaches y equals x. So now why am I pointing that out? Well, if you graph this line, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, it does this. Now I didn't draw a very good picture, so it seems that these are going to cross way down here, right?
Yeah.
But if I think about this, what's the slope of this? Well, negative 1, but yeah. Negative 1 slope. What's the slope of this? Negative 1. So if I'd been a better drawer, this is where maybe I asked Mr. Desmos to help me
To
out.
assist me.
What? To assist? Exactly, I say, Desmos, I beseech thee. If I graph x squared minus y squared equals 4, it's coming up here. No, don't you worry. Okay, so then, okay, great. And then I graph x plus y equals 5. And then I ask, do these ever cross? Doesn't. I think that's pretty fascinating that they don't cross. They just never cross. It's kind of interesting. They never cross up here either. That's the thing about asymptotes. So it turns out, incredibly, that there's, when I drew this originally, it would have been very reasonable to go, well, either they're going to cross up here or cross down here, but it turns out because of the diagonal asymptote, they're actually only going to cross one time. There's only one pair of numbers that works. So I don't know. I think that's kind of interesting. How are you doing for time?
I don't know.
We can do one more little thing. Plenty of time. Okay, so last thing I want to discuss today would be number 5. Before I move on, does anyone have any questions at all? Like anything we've covered so far? Any points of confusion? Okay. All right. So number 5, we can maybe just do this verbally. So, okay. So there's some function out there, y equals f of x. It contains the point 14.5. First of all, can anyone translate that into functiony notation language? Like, if I say that the graph of y equals f of x contains the point 14.5, very good. F of 14 equals 5 is equivalent to that statement. Okay? So let's look at A. Maybe I do want to write some stuff on the board because I think there's really two good ways to think about this question. There might be more. I just personally can think of two. The first one is, what happens when you have a graph and you replace the x with an x minus 4? Visually, what happens to the whole structure? Goes right, shifts to the right 4 units. So if this graph used to have, so let me just draw a little picture here. So my first way of thinking about it is, graphically. So if I have the point 14.5, and f could look like anything, say f looks like that, whatever. Well, if that's f of x, then the graph of f of x minus 4 would be, let's see if I can do this. I don't know if I believe in myself, but that looks decent, I guess. The whole thing would get, every single point gets shifted to the right 4 units. So where's this point then? 18.5. Cool beans? That's the answer. Now that's method 1 that I think makes sense. Method 2 would be, let's say I am a bean. I know one thing. What's the one thing I know in my bean life? That f of, I must write it wrong. I only knew one thing and I wrote it wrong. It's exactly what Rafe said earlier. Imagine that we only know one fact in the whole world. That's the only thing we know. We know nothing else. Okay. Well, if I know that, and you ask me, okay, well, now I want to go f of something minus 4 equals something. Well, I only know that if this thing is 14, then this thing gets to be 5. That's all I know. So what does x have to be in order for me to be able to use the one thing I know? X would have to be the number 18, and then f of 14 has to equal 5. So what I've shown is that on my new thing here, when x is 18, y is 5. Again, 18.5 is the point on the graph. Cool beans? Okay. Okay, so let's end it there today. And try to take the next couple minutes. I know class is over pretty soon, but try to answer a couple more. 1 or 2 more questions. And yeah, we'll take off. Oh, the computer, I think, lived. It went the whole time. Yay.